Thank you, Noga. As Noga said, I'll talk today about interlacing families and how they apply to the Kadison Singer problem. And this is joint work with Dan Spielman at Yale and Nikhil Srivastava at Microsoft India. And at the time, I was sponsored by the NSF. OK, so the goals of the talk are to give a brief history of Kadison Singer and its relatives, to convey how we went about attacking the problem, introduce a technique for showing the existence of combinatorial objects that we call the method of interlacing polynomials, to introduce a class of polynomials we call mixed characteristic polynomials, and then use these to prove two known equivalents of Kadison Singer, and then discuss some related open questions. And mostly in this order, but there will be some. And please interrupt if there are any questions at any time. I don't remember what I did 20 minutes ago, let alone 40 minutes ago, so please just interrupt. So brief history. So here you are at the beginning of quantum mechanics. Well, here Paul Dirac is at the beginning of quantum mechanics. And he's sort of writing the first textbook about principles of quantum mechanics. And in his textbook, he writes this particular part on how to introduce a representation of a quantum state in practice. And what he says is that you first measure what he calls a complete commuting set of observables. And that's essentially you go through all of the observables that you're interested in, and you measure one, and then you measure another one if it doesn't introduce any uncertainty principle. And then you just keep adding them on, and you keep measuring what you can do without introducing any uncertainty. Then he says you express the observed probability distribution as an ensemble over pure states, which is essentially you have this matrix of measurements, and you diagonalize it. And then you generalize this to the entire system. And I should say that this predates the formalization of quantum mechanics using C-star algebras, which happened in the 40s. So that's 30 years later. Kadison and Singer were reading this book, and they were deep in the C-star algebra formalism. And they looked back at what he wrote here and said, I'm not convinced that this generalization to the entire system is actually unique. So, I make these measurements. Do I ever have to make a choice as to which generalization I use? And their precise question is this. If A is a discrete maximal abelian subalgebra, the discrete is important, of the bounded linear operators on a separable complex Hilbert space, and rho is a pure state on that subalgebra, is the extension, which if you start with a pure state, the extension will be pure, of rho prime to rho, of rho to rho prime, is that unique? And the pure states here are the rank 1 operators, plus it turns out a bunch more. So when you build this this space of bounded linear operators, you get that there are all of these other extremal points in your algebras, and these are the ones that Dirac ignored. So if you are just moving from rank 1 to a bigger rank 1, a rank 1 in the smaller space to a rank 1 in the bigger space, it's trivial because you just add a bunch of zeros and you say that this rank 1 moves to that rank 1. But the problem is you have all of these other states which now exist in your construction, and it may be that one of those states projects down onto one of your rank 1 matrices in the smaller space, at which point when you make that measurement, you have no idea whether you should be extending up to the corresponding rank 1 state or whether you should be extending up to one of these bizarre axiom of choice states. And the reason that this discrete adjective here is very important is because Kadison and Singer showed that, in fact, it's not true in the continuous case. And their example was the Hilbert space L2 of 0, 1. I think it's just the, I think it's just the multiplicative functions or something like that. The construction is easy. I think that showing that the generalization is not unique is probably not. I mean, I don't know it offhand. Okay, so in an attempt to resolve Kadison and Singer's question, a number of interesting equivalences were shown. One of which was known as Anderson's paving conjectures. Bourgain and Safiri began working on this and came up with their own set of conjectures in 1991. Weaver was working on this and came up with what he called KSR and KSR prime conjectures. It turns out that in a completely unrelated situation, they weren't actually working on this problem, but there's what's known as the Feistinger and R epsilon conjectures that appear in frame theory that have been shown to be equivalent to this.
All of those are finite dimensional already?
These are all, still finite dimensional. And other results were known to imply Kadison Singer. So there was another collection of conjectures known as the Ackermann-Anderson projection paving conjectures, which are known to be stronger than Kadison Singer, to imply Kadison Singer, and KS2 in particular, one of the KSR problems, is also known to imply Kadison Singer. And here's a quote from a book that was written in 2013. Most people today seem to agree with the original statement of Kadison Singer that KS will have a negative answer, and so all equivalent forms will have a negative answer as well. And so much of the research that had been done was in anticipation of this being negative. So let me tell you what's really at the heart of all of these conjectures. And let me tell you what a Parseval frame is. So a Parseval frame is a collection of vectors whose outer products sum to the identity. And obviously, an orthonormal basis is a Parseval frame, and Parseval frames are constructed to act like orthonormal basis, but it sort of allows you to split the work over more vectors. So you might want some redundancy in your measurements, and so you don't use just n vectors, you use maybe 2n or 4n or something like that. But the idea is that you want them to reconstruct the original vector.
Why are orthonormal bases Parseval frames?
Because if you sum EI transpose over all of the I, it's the identity.
EI transpose just is a matrix with 1, 1, all the rest are 0.
Oh,
Yeah.
sorry.
And everything, all other rotations are just rotations of that.
And that's IJ, oh, V1 through VM.
Yeah, V1 through VM, and you're trying to, you're trying to give a redundant version of an orthonormal basis. So an orthonormal basis is itself a regular simplex centered at the origin. If you properly scale everything, it is a Parseval frame. If you take two Parseval frames that you have and you union them together and then scale them, that becomes a Parseval frame. And in fact, if you take any vectors that you're interested in and transform them by the square root of their inverse, that turns your collection into a Parseval frame as well. And at the heart of all of these conjectures is this question. I have this Parseval frame. I'm building the identity using this redundant system. Can I partition it into two parts such that each of the parts is almost Parseval? So I have one set which is sort of almost half of the identity and the other set which is almost half of the identity. And in general, the answer is no. And the problem is that there may be huge vectors, right? Take the orthonormal basis case. Like if you have a vector that's the only vector moving in that direction, you can't put it in both sets, so one set is going to be left without, one set is going to have 0 in that direction, the other one's going to have 1 in that direction. So the question then becomes, what if all of the vectors are all bounded in size? So I have a bunch of small vectors which make up my, my Parseval frame. Then can I partition them into 2 pieces so that the 2 pieces themselves act like half of a Parseval frame?
So when you say bounded size, are we talking about the norm of the vectors?
The norm of the vectors, yes.
Relative to dimension. Because the example you gave, the orthonormal basis, are also at 1.
So you could ask relative to the dimension, and we'll see that. So what if I choose randomly? So I have this collection of vectors which sums the identity. One thing you can do is just pick a random collection of them and see how good it is. And Joel Trop in 2011 showed that if you pick this uniformly, with very high probability, you will get something that is almost Parseval, assuming that the norms of your VIs are less than or equal to some constant over log D, where D is the dimension. Okay? And this uses matrix concentration inequalities similar to Rudelson and Elseway to Winter. This way. And in fact, this is known to be best possible for the random case, and it's tight when each of the VIs is a scaled elementary basis vector. It turns into a balls and bins problem.
But in the example, you said it in the example of orthonormal vectors, no choice is good. So how can it be decidable basis?
Because in the so in this case, in the orthonormal basis case, all of the VIs have length 1. And here he says if all of the VIs have length C of epsilon over log D, then he can pick it randomly. And to your point, the goal of this talk is essentially to remove this log D factor. So we want to find a universal constant such that if all of our VIs are less than or equal to that constant, then I can partition these things into 2 pieces.
So then I don't understand what you mean by partition 2 pieces if they're all almost. What is almost?
So almost will be as a function of this epsilon.
So the difference from I to the matrix you actually get.
The difference between 1/2 of I and the matrix that you get is going to depend on how big your vectors are.
And the difference in 2 in 3
Difference in, so this is our, so we're building a matrix, so we're looking at the spectral norm, like the eigenvalues. Okay.
For the random, with the log D, it's very simple, right?
So it requires one of these sort of matrix concentration inequalities, which are.
So let's say if I would replace log D by some other function of D, at some point it becomes trivial, right?
Right. So yeah. And log D was the best known, and for a random pick, you can't do any better.
The main thing is to be independent.
You needed to, yeah. So for the thing that we're going to talk about, I needed to be independent of D.
I'm sorry, you said spectral norm, but a univolt matrix has all eigenvalues 1. So
Yes. So I'm trying to split. So I started out with something that's the identity. So all of the eigenvalues are 1. I want to split the vectors into 2 groups so that when I look at the eigenvalues of this group, they're very close to 1/2. And when I look at the eigenvalues of this group, they're also very close to 1/2.
you could have eigenvalues 1/2 without being the identity. You're upper triangular with all 1/2s down diagonal.
You could be, but in our case, we're summing over semi-definite. Yeah, we're summing over these symmetric matrices. So there seems to be a slide missing where I actually told you what KS2 was, but let me try moving on anyway. Okay, so what you need to know for this talk, Kadison Singer asked some fundamental question about the mathematical foundations of quantum physics. There are a bunch of other problems that are equivalent. One such equivalence is this KS2. And the heart of the question is whether a Parseval frame with vectors bounded in norm by a constant can be partitioned into two almost Parseval frames.
The 2 is because you partition to 2. That's the KS2.
That's what the 2 in KS2 is, yes. And in this talk, the goal is to show a positive solution to KS2, and therefore all of the equivalent forms. Why are you not working? OK. So notations and simplifications. Throughout this talk, most of the talk, all of these things will hold. So D is always going to be the dimension of our vector space. M is going to be the number of vectors. V without a hat is going to be a deterministic vector. And V with a hat is going to be a random variable that takes these deterministic vectors as its possibilities. And capital V's are going to be matrices. You are not happy with me. And for the purpose of this talk, all of my vectors are going to be real vectors. Although the proofs carry over to complex vectors, the only difference is you replace the transpose with an adjoint. Oh, now you're. And in this talk, all of the random vectors will choose from two possible values, although the proofs can be extended to any kind of random vector.
So the proof is they extend to normal matrices as well?
So what do you mean? I mean, so the way we're building our matrices, they're always going to be symmetric.
Right, but so you could have the spectral norm if you assume that the A and A dagger commuted.
Right?
So I was wondering whether that would make no difference here.
So the problem we're solving, so let me tell you the problem we're solving. Okay, here's our main theorem, and this is why you'll see that all of these are just going to be symmetric matrices. Here's our main technical theorem. If epsilon is greater than 0, and v1 through vm are independent random vectors, such that the sum of their expected outer products are the identity, and the expected norm squared of each random vector is less than or equal to epsilon, then there exists an assignment vi such that the spectral norm of the sums of the vi transpose are less than or equal to 1 plus square root of epsilon squared. So if in expectation all of your vectors sort of act like the identity, then you can find some sub-collection of them which acts close to the identity with some factor of epsilon, which depends on the length of the vectors.
So what we should be looking at is the second display where there's an epsilon and nothing depending on D.
Correct. We need the epsilon to be yes, and this to not depend on D, right? So the way we're building our matrices, like we always just have symmetric ones. And in this talk, I'm going to assume that epsilon is less than 1/4 and prove it for 1 plus 3 square roots of epsilon, which is a slight weakening, but it makes all of the constants easier to deal with.
So do you want the norm to be lower bounded by 1 minus root epsilon?
So for our case, where we're splitting it up into two groups, that's actually not needed because the smallest eigenvalue of the other group is going to be the biggest eigenvalue of the first group. So for us, this is not going to be an issue. And in practice, I don't think. So in practice, it turns out to be sort of much harder to bound both of them at the same time. So we actually need, for our purposes, we need this trick that it splits into two.
Where do we see the splitting into?
Here, so to actually prove KS2, we'll need to split into two. But for the theorem, there's no.
This theorem implies KS2 or what?
This does imply KS2, and I'll show that. And there was supposed to be a slide that showed you what KS2 was, but I seem to not have one.
It will be this way when each random vector takes only 2 vectors.
So I'm going to prove this for the case when each random vector takes only 2 values, but the proof extends to they can take any number of values.
And is this
So for some epsilon, so for like epsilon 1, at least in our case where we're splitting it up into two things, it's trivial because you can't do any worse. Because taking all of them is going to give you something that has norm 2, and then any subset's going to have less than that. But
So only small epsilon.
only small epsilon makes it interesting, yeah. So attacking the problem. So despite not telling you what KS2 was, let me tell you that what's nice about what's nice about our formulation that's somehow not nice about what Kadison Singer is. And one is that we're able to translate this into the world of polynomials. So given a collection of vectors, I can form the sum of their outer products. And then the maximum eigenvalue of this matrix is the largest root of the characteristic polynomial. So instead of dealing with matrices, I can start asking questions about this special class of polynomials. The second thing that's nice about it is this formulation is sort of ripe for experimentation. So I don't know how to take random collections of subalgebras and extend them to Hilbert spaces, but I can take random collections of vectors and form their characteristic polynomials and then see what happens. So in particular, I can try optimizing over various collections of vectors. I can see what the best case scenarios are, the worst case scenarios are, the average case scenarios are, and all this stuff. So this is somewhat of an advertisement to people who don't use computers that life sometimes it helps to use computers. So that is what we did, and let me just give you the observations that we made. So the first observation was that the expected characteristic polynomial, so I take all of the possible ways of choosing my vectors, there's 2 to the m of them. I take each one, form the characteristic polynomial, take the expected value of it. They always seem to be real rooted. This was just an observation. The second observation was when we looked at all of the possible values of our random matrix, which satisfy the hypotheses of our theorem, there always seemed to be one whose characteristic polynomial had a smaller largest root than the expected characteristic polynomial. Yes?
The probability measure is like half-half?
So in our experimentation, we did half-half, but it turns out it doesn't matter. Yeah, it always turns out to be real rooted. Observation 3. I'm sorry?
Okay, you mean that it had a smaller, largest root than the largest root
Of the expected, okay, yes. So somehow there was always something that did better than the expected.
Okay.
The third observation was when we looked at these expected characteristic polynomials and optimized over them to see what the worst case scenario was, they always seemed to have the maximal largest root when all of our vectors were the same size, and when all of our random vectors, actually their expectation was the same. And observation 4 was when we looked at this case where all of the vectors were the same and the random vectors were epsilon over d times the identity, the polynomial, the expected characteristic polynomial, turned out to be what's called an associated Laguerre polynomial. And these are classic orthogonal polynomials that have been studied for a long time, and in particular have very nice bounds on their roots, very close to what they actually are. And the bounds that are true on this Laguerre polynomial satisfy the bounds that we were hoping for. So experimentally, at least, the worst case scenario that we could find seemed to do what we needed it to do, and so we sort of thought, maybe the less worst case scenarios do it as well.
So what did you do experimentally? What was M? What was D? How did you choose?
So D. So I'm actually not sure because Dan has this entire suite of optimization things that he's created. But D tended to be very small because we couldn't really compute things very large. So D was usually 5 or 6. And M was something between, let's say, 10 and 40. But yeah, so I'm definitely not saying that this was like overwhelming evidence. That there certainly could have been small dimension factors that were going on, but it sort of directed our approach.
So the vectors are sampled here uniformly?
I mean, so we sampled them in a whole bunch of different ways. So, for this one, for the worst case, so it turns out to not really matter unless all that really matters is that in expectation your outer product is this, and that the expected size is the same.
It's enough to know these things to compute the expectation of the polynomial.
Yeah, and we'll see that later, that it turns out that the vectors you use and the probability distribution you use is irrelevant to the expected characteristic polynomial. Okay, so the point of this is that it suggests an approach. If we could somehow bound the largest root of the expected characteristic polynomial over the set of random vectors that satisfy the hypotheses of the theorem, and then show that there always exists some assignment such that the largest root of that assignment is smaller than the largest root of the expected one, then this would prove our theorem, right? The expected characteristic polynomial would be our bound, and we are just going to show that we can always find some assignment which does better than the expected characteristic polynomial. We don't need strictly smaller, and in fact, yeah, yeah. So then, right. Okay. So, yes.
Is it clear why the expected characteristic polynomial should be real rooted?
No. So it should not be clear why it's real rooted. It should not be clear that it has anything to do with anything, to be honest. I mean, when you add polynomials together, there's no reason why their roots should have anything to do with the original roots. So the fact that, so my claim that there always exists an assignment such that this thing is smaller or larger than this thing, first of all, assumes that there's some relation between the two of them, and that's also not true. So there should be nothing clear about anything that we've done so far, other than this approach matches essentially what our observations were. And so if we could magically do these things, then that would solve the problem. And that's what we're going to do.
No, but what I meant by that is that could you describe these random experiments on the vectors as operation on the underlying matrices? So real rooted to me suggests you're looking at some other symmetric eigenvalues for some other underlying symmetric matrix.
Right. So that's sort of what we're working on now. So we don't have any way of really understanding what those, what the actual matrix is that would satisfy these things. Okay, so I'm going to start with part 2, this idea that I can relate one of my assignments to this expected characteristic polynomial. And the main idea is to define a process by which we pick the assignments one by one and try to understand how now conditional expected characteristic polynomial changes. So also back to one of the things that you had said, it has been told to me since we've proved this that in fact the expected characteristic polynomial is not only not supposed to be related to any of the things, it's also notoriously bad for for showing how these things behave. And in fact, in random matrix theory, sort of the rule of thumb is to never look at the expected characteristic polynomial because it will lead you astray. So despite that, we'll do it anyway. Fortunately, we didn't know any random matrix theory. So let me talk about interlacing families.
It connects to the special term here.
Yes. So right now, I just need to establish some notation to help keep track of the assignments that I'm going to make as we go along. So I'm going to define what's called a choice vector, sigma, which is 0, 1 to the m, where sigma I corresponds to whether this random vector took the first choice or the second choice. And I can reference the characteristic polynomial of any fixed assignment using this way of notating it. But I'd also like to define what I call a partial choice vector, which is sigma prime in 0, 1 to the k. And the corresponding polynomial will be the conditional expectation over all of the things that I haven't chosen yet. So I'm forming like a martingale here. And you should note that the P empty set, which means that I haven't made any choices yet, is the expected characteristic polynomial over all of the choices. And that's the thing that I claim that we're interested in. OK. So I'd like to go from a full choice vector all the way to the no choice vector. And the way you do this in regular martingale theory is to have these forward-backward relations. So we have this relation that P sigma prime of x is P sigma prime 0 of x times the probability that vk plus 1 takes 0, plus P sigma prime 1 of x times the probability that vk plus 1 takes 1. And already now we've reached our first major issue. And the problem is that adding polynomials, because we have now a linear combination of polynomials, adding polynomials is a function of the coefficients inherently. And we're interested in the roots. And in general, it's pretty easy to get the coefficients from the roots. You just multiply out x minus the roots. But it's not particularly easy to get the roots from the coefficients. That's what Abel's theorems tell us and things like that. So our approach is going to be forget that this is an issue and see what we can prove, and sort of just live in denial for the moment. And here's a lemma. And it'll be sort of the main lemma. So let f and g be monic polynomials. And let's assume there exists a point C, which I'm going to call the anchor, such that f and g each has exactly one real root larger than C. I'm going to call these roots the extreme roots. Then I claim that the largest real root of f plus g lies between these extreme roots. And the proof is by picture. So here is our anchor. And since f and g are both monic, that means they end positive as x goes to infinity. And because this anchor is here, we know that each of these polynomials has exactly one root larger than the anchor. So they must both cross here and be negative at the point where the anchor is. And so here I have a sum of polynomials which starts out negative and ends out positive. And so somewhere in between it has to be 0.
Where did you use the anchor?
The anchor is what prevents this from coming back up and being possibly a positive plus a negative. So I need to force both of these to be negative at the anchor. And if I allowed this thing to have another root here, it could not. And here's actually an example. So without C to anchor, here are two polynomials where this thing has actually two roots which are larger than the largest root. So there's no C. And when you add them together, what you get is a polynomial whose largest root is less than all of these other roots.
Does f plus g have only one root between the anchor and the infinity?
So yeah, so for the case of 2, the answer is yes. For the case of more, it could be no, I think.
In this picture, do we see f plus g or half f plus f times g? Do we see the sum of the
No, we don't see the sum.
So it's I mean, as far as the roots go, it's irrelevant, right? You multiply a polynomial by a constant, like it's going to be the same. So it's going to have the same roots.
Again, the important thing in this picture is that it's the maximum root of f. We know from the picture that g is still negative, and because of this, the sum is negative.
And at infinity, it's positive, so somewhere in between it has to be 0.
I mean, you can't have more zeros, right? If it oscillates along that like then the sum of
Actually, okay, yeah, I think you're right, yeah. So it can be bigger. But the point is that, right, okay. So the f and g has to lie between these. Okay, so I've just told you what happens if I have real roots. So I can say something about the situation where we have real roots, but not necessarily complex roots. And that's a problem, because if my polynomials had complex roots, I would essentially have nothing to say. But if you recall observation 1, the expected characteristic polynomials seem to always have all real roots. And if this was true, and it was true in more generality, it was sort of true for all of the polynomials we needed to look at, then I'd be in good shape because I don't need to deal with complex roots because all of the roots involved would be real. And while our original polynomials, which are characteristic polynomials of Hermitian matrices, are real-rooted, in general, when you sum these things together, they're not necessarily real-rooted, right? You can sum these two together and you get something that has no real roots. But let's go back to our equation and see what the lemma says about it. We have this equation. We have this lemma, and what the lemma tells us is that if p sigma prime happens to have all real roots, and if p sigma prime 0 happens to have all real roots, and if p sigma prime 1 happens to have all real roots, and there happens to be some anchor c, which is anchoring the largest roots of p sigma prime 0 and p sigma prime 1, then we know that the largest root of p sigma prime lies between the largest root of p sigma prime 0 and the largest root of p sigma prime 1. That's what we know. That's what the lemma tells us. So let's forget about the real rootedness for a moment, and let's just worry about c, because we're going to need to find a c.
If this would be okay, then you would choose the one that has a smaller, largest root, and you would continue.
Correct, yes. And I'll get to that in a second. So let's worry about c for the moment. I'm going to need to find these anchors which guarantee that I have this structure. Okay, so let me define interlacing polynomials. Let p be a real-rooted polynomial of degree n, and q a real-rooted polynomial of degree n minus 1, where these are the roots and they're ordered as such. I'm going to say that q interlaces p if in between every two roots of p there is some root of q. Okay, the roots of q are separating out the roots of p for us. And as an example, p prime, if p is a real-rooted polynomial, p prime interlaces p. That's essentially Roll's theorem, that at some point between two roots you have to have your direct derivative is 0. And if p has no multiple roots and largest root r, then I can pop off the largest root and shift my polynomial over a little bit, and that will also interlace the original polynomial. So I want to say that two degree n polynomials p and r have a common interlacer if I have this q which interlaces both p and r simultaneously. And the way to think about it is the roots of q split up r into n different intervals, and each of those intervals needs to contain exactly one root of p and exactly one root of r. Something like this. And the punchline here is that if p and r have a common interlacer, say q, then q provides us the anchor that we need, right? The largest root of q is going to be such that both p and r have exactly one root which is larger than c. And so this will allow us to use the lemma. Is that clear? Okay. So let me define interlacing families, and it's essentially exactly what we need in order to be able to do all of the things that we want to do. So we say that p, which is indexed by some sigmas, is an interlacing family if for all partial assignments sigma prime, we have that each polynomial p sigma prime is real-rooted. So we need real roots for all of our polynomials. And the polynomials p sigma prime 0 and p sigma prime 1 have a common interlacer. And that allows us to relate the roots of this to this. And the corollary, as Noga had mentioned, is that if p sigma forms an interlacing family, then I claim that there exists an assignment, sigma naught, such that the largest root of that assignment is at most the largest root of the expected characteristic polynomial. And the proof is to start at the expected characteristic polynomial and walk backwards. So you have your expected characteristic polynomial. You know that one of the two assignments that you can make for the first vector has a better largest real root. So pick that one. Now you have a choice to make about the second one, the second assignment. So pick the one that continues to cause your largest real root to go down. At the end of the process, you've, yes?
P sigma prime was like some average of P sigma 0 and P sigma 1?
Yes, it was.
You mentioned like if two polynomial has a common interlacer.
Yes.
Then the sum has real root. All the zeros of the average is real root.
So no. So I don't. So even in order to have an interlacer, in order to define interlacer, I have to assume that all of these things have all real roots. Otherwise, it doesn't make sense.
So if sigma prime 0 and sigma prime 1 have common interlacer and have real roots, does it imply P sigma prime have real roots?
Yes, and that's essentially what we're going to show right now. And also the reverse as well. So here's, for the interlacing, we have, we can essentially get the interlacing for free in our situation, because there's this lemma, which is folklore, but we found it in Fisk, which says if f and g are polynomials at the same degree, such that every convex combination is real rooted, then f and g have a common interlacer. So that's sort of the converse of what you were asking, right? Yeah.
The common interlacer is somehow more than you need, right? You only care about the anchor.
I only care about the anchor. It turns out in order to produce an anchor, we actually needed all the real roots, yeah. So recall again our equation. This is p sigma prime is some convex combination of these other two. So if we were able to show that the p sigma prime is real rooted, independent of the probabilities, then we get the interlacing for free. Right? So I can sort of get rid of at least one of my constraints that I need to satisfy. So now we need to start understanding real rootedness. Okay, so where to start? The problem with real-rooted polynomials is that it's kind of hard to see how you get from one real-rooted polynomial to another. And that's sort of signified by this parking garage where there are cars on different levels, but it's not clear how you get from level to level. Unless you consider them to be a projection of a higher dimensional object, in which case sometimes you get this nice structure which shows you how these things connect to each other. Unfortunately, there have been a number of recent advances in understanding real rootedness using this idea and using what is called the theory of real stable polynomials. And the real stable polynomials are a multivariate extension of real rooted polynomials. So a polynomial p is real stable if all of the coefficients are real. That's what the real means. And the stability part is that p, when you plug in coordinates for which all of the imaginary parts of those coordinates are greater than 0, is never 0. So you don't have any roots for which all of the coordinates lie in the upper half plane. Some important properties. Firstly, univariate polynomials are real rooted if and only if they are real stable. And that comes from the fact that for univariate polynomials, complex roots come in pairs. So if you have any complex root, in particular, you have one in the upper half plane.
Sorry, what does this notation mean? Something with ZI?
This is the imaginary part of ZI.
Oh,
And real stable polynomials are closed under substitution of reals. So this is a non-trivial fact. So if I told you that they were closed under substitution of things that lie in the upper half plane, that's trivial. But to show that it also is also closed under substitution of reals, you need to use a property of the fact that stable polynomials are closed under limits, and then to show that, you just show that there's a limiting sequence of all upper half planes. And this is known as Hurwitz's theorem. And these are very similar to what are called hyperbolic polynomials, if you've come into contact with those. Okay, so Borchet and Brandain have sort of this program that they've been following for a while, where they've been developing techniques for understanding real stability. And in particular, I'm going to use two of their lemmas. The first is that if A1 through AM are Hermitian positive semi-definite matrices, and X1 through XM are variables, then this polynomial is real stable. And this comes from the fact that you can take the positive square root and factor it out. And their other lemma is that if you start with a real stable polynomial and you subtract off one of the partial derivatives, that's also a real stable polynomial. And that has to do with Rolle's theorem again, that you can.
So the other way around, every real stable polynomial could be expressed as a determinant of some.
So when m equals 3, the answer is yes. When m is bigger, the answer is no. The m equals 3 case is known as the Lax conjecture. And it was proved by Helton and Vinnikov. Well, essentially proved by Helton and Vinnikov. And for higher dimensions, for higher level m's, it's known not to be true. But in most cases, it actually turns out that 3 is all you really need, because you sort of lose, well, I'll go into that later. Okay. So now I need to understand our polynomials. But fortunately, our polynomials have a nice general form. So let v1 through vm be the random vectors, and let ai be the expected outer product of each random vector. My claim is that the expected characteristic polynomial is, you start with this polynomial, determinant of xi plus ziai. You apply this operator to it for each I, and then you set all of the zi's equal to 0. And one thing to notice is that the expected polynomial does not depend on the vectors, and it does not depend on the probabilities. It only depends on the expected outer products. And for that reason, we call this a mixed characteristic polynomial and denote it as this to sort of remind you that the original probability distributions and such really make no difference. It's only these expected outer products. Essentially, because of the independence, the expectation factors in. And I claim that there are a world of mixed characteristic polynomials. In particular, every polynomial we've seen so far in this talk is a mixed characteristic polynomial. So a normal characteristic polynomial is a mixed characteristic polynomial. You just pick up this random vector to be this vector with probability 1. The expected characteristic polynomial is certainly a mixed characteristic polynomial. You just plug in the expected outer products of each vector. And the partial assignment polynomials are also mixed characteristic polynomials, because for the first collection, you tell it what you've picked, and then for the rest, you show it the expectation. Okay, so putting it all together, my claim is that mixed characteristic polynomials are real-rooted. So by the first lemma of Borchet and Brandain, we know that this is real stable. By the second lemma of Borchet and Brandain, every time I do this operation, I maintain real stability. And then the last thing I do is plug in a bunch of numbers, and since real stability is preserved under substitution, what comes out is real stable as well. But what comes out is univariate, like it's only a function of x, and any real stable polynomial which is univariate is real-rooted. And so all of our mixed characteristic polynomials are real-rooted. So hopefully that answers your question. The probability distributions are irrelevant. And as a corollary, our polynomials form an interlacing family because all of our polynomials were mixed characteristic polynomials, and all mixed characteristic polynomials have real roots. Okay, so a quick review of what's happened. We defined interlacing families and showed that any such family has a polynomial whose largest root is smaller than the largest root of the expected polynomial. We argued that for our polynomials, the interlacing condition was implied by the real rootedness of the partial assignment polynomials and the recurrence equation. We defined mixed characteristic polynomials and showed that our partial assignment polynomials belong to this class. And then we showed that this class of polynomials were real rooted by using Borchea and Brandin's theory of real stable polynomials. Yes?
To show interlacing, you wanted to show that by any convex combination of these polynomials, it has real stability.
Correct.
Which slide was that one?
So it turns out that, right, so we got that for free because think about what our our recurrence equation says. It says P sigma prime of x is P sigma prime 0 times some probability plus P sigma prime 1 times some probability, which is a convex combination. So if I could show that this was real rooted for any version of these probabilities, then that's my convex combination. So I sort of did double duty here by being more general than I needed to be. Any other questions? Okay, so what are we left with? We're left with bounding the largest root of the expected characteristic polynomial. If we could do that, then that would give us the bound that we want on the assigned polynomial. So bounding roots. So what do roots of multivariate polynomials look like? Well, rather than having points as their roots, they have zero surfaces. Or varieties if you're an algebraic geometer. And they sort of look like this. I want to define what I call being above the roots. And the idea of above the roots is that you're in this cone right here. So I'm going to say that that W is above the roots of P if I take some positive orthant and root it at W, I never cross the zero lobes. Right? So essentially this lobe contains a copy of the positive orthant. I can move in any positive direction and never touch that zero. The diagonalization of P of a multivariate polynomial is the univariate polynomial where I set all of the things to be the same. And that looks like this. So here's this multivariate polynomial that has these real rooted that has these lobes, and if I then take the diagonalization, that's a univariate polynomial, and the roots are exactly where it intersects those lobes. Okay? So fortunately, I can transform this target polynomial into a diagonalization. So this was our original polynomial, and the proof is not very hard. You substitute y equals zi plus x. So rather than plugging in z1 through zm is 0, we plug in y1 through ym equals x. So I have this nice diagonalization form of the polynomial. And okay, recall what our actual interest is in bounding the roots of this polynomial. In the case that the expected outer product is the identity and the expected norm squared is less than epsilon. So given what we know about mixed characteristic polynomials, I claim that this is equivalent to showing that for some t, that t times the all ones vector is above the roots of this thing, whenever sum over your AIs are the identity and the trace of the AIs are less than or equal to epsilon. This was just the substitution, and then saying the largest root is bigger than y1 through ym says that is the same as saying t times the all ones vector is above the roots in the lobe. And how are we going to do that? We're going to apply the operators one by one and see what happens to the roots. And the see what happens is going to be measured by what we call a multivariate potential function that we're going to use to help understand how things behave. And the one we're going to use is the partial derivative of the log of our original polynomial. So what are the important properties of this? Well, first of all, it blows up whenever a variable gets close to a zero surface of P. It's monotone, non-increasing for any w that's in this lobe that's above the roots of P. It's convex at any w that's above the roots of P. And the idea is that it measures the amount of cushion we have in a given direction. So the lower the potential function is, sort of the further away we are from all of the dangerous crossings that we might have. And it's a generalization of a univariate potential function from Batson, Spielman, and Srivastava, which is if you have a univariate polynomial, they use just the univariate derivative of the log, and that's 1 over x minus ri, and that sort of shows you all of these properties. Okay, so I call this the testing the water lemma, and the lemma is if P is real stable and w is above the roots of P, and I have this bound on the potential function, then my claim is when I do this operation that w stays above the roots of P. And the proof is that since phi pi is non-increasing, I get that phi pi of w plus t is less than 1 for all t. And therefore, this is just plugging in the definition of phi pi. Partial over partial zi of pw plus t is less than pw plus t, which rearranging gives you that 1 minus partial over partial zi of pw plus t is greater than 0. And that's true for all positive t, which is the definition of being above the roots. Okay? And what's happening? So when you apply this operator 1 minus partial derivative, your lobes start encroaching upon you. And what this previous lemma says is that if you have enough cushion in the beginning, when this lobe encroaches on you, you're still on the right side of the lobe. So if phi pj is less than 1, then we're still above the roots after the shift. The problem is that we've now screwed up the potential function, right? We're trying to measure how much cushion we have, and now if I just allow this thing to encroach, I have no idea what my new potential function is. So, and in particular, it is going to affect the potential function in other directions, so we're going to need to do something a little bit more complicated. And so this is what I call the jumping in lemma. So the lemma is if P is real stable, and you start at w, which is above the roots of P, and you're able to quantify how far away you are from 1 with the potential function, then w is above the roots of 1 minus partial p, that was the other lemma, and we can get a bound on what happens to the potential function in the other directions. And the proof uses the convexity that I mentioned above of phi pi. And how do we interpret this? Well, if I apply this operator, the lobe becomes closer. And if I know that phi pj is less than 1 minus 1 over delta for some delta, that essentially tells me that that's how far I need to move in order to maintain the cushion that I had before in each direction. Okay, so now let me give you the proof of the bound. And the theorem is that 1 plus 3 square roots of epsilon times 1, the all ones vector, is above the roots of this thing. Right? That's equivalent to saying that 1 plus 3 square roots of epsilon is an upper bound on the roots when I diagonalize this. And the proof is I start with Q0. And note that Q0 is a sum of positive semi-definite matrices times some variables. So as long as I plug in some t times 1, where t is greater than 0, this is going to be above the roots, right? Because when I move in any direction, it's going to get more positive semi-definite, and it's never going to get to 0. Well, this uses also the fact that the sum of the AIs is I. So I could use anything to start with. I'm going to use t equals the square root of epsilon. And the reason is because that's sort of the amount of cushion I'm going to need in order to be able to show that I maintain my cushion everywhere. So if I started really close, this lobe is going to encroach upon me, and I'm not going to be able to say anything about what happens. OK, so set W0 equal to T1. And when you do the calculation, you get that phi I of Q0 is square root of epsilon. So that's the cushion we have in each direction. And this satisfies our cushion lemma. Remember, there's like this 1 minus 1 over delta. So you solve for delta. And for any delta greater than 1 over 1 minus square root of epsilon, you pick this cushion lemma works. So I'm going to pick delta equals 1 plus 2 square root of epsilon. And that's where the epsilon less than 1/4 comes in. And then I apply my operator, 1 minus partial z1, and then move delta in the direction of e1. So what happens? By the lemma, I'm still above the roots. And my new polynomial, in all of the other directions, I still have the same, at least the amount of cushion that I had before. So I just keep doing this. So I do this for I equals 2 through m, using the lemma each time. At the end of the day, I've done all of my operations that I need to do. I've moved delta in every single direction. Remember, delta was 1 plus 2 square roots of epsilon. So I've moved 1 plus 3 square roots of epsilon, and I've remained inside of this lobe. And so in particular, I'm above the roots as required. OK, so second intermission, a quick review. What have we done? We defined interlacing families and showed that any such family has this nice polynomial that's better than the expected polynomial. We showed that our polynomial formed an interlacing family by showing they were mixed characteristic polynomials. Then we defined a multivariate barrier function to help us understand the evolution of the zero surfaces of multivariate polynomials. And we used this to show that for our polynomials, the largest root of the expected characteristic polynomial was at most 1 plus 3 square roots of epsilon. OK, so now let's prove the theorem. We've proved our main technical theorem for when epsilon is between 0 and 1/4. And we have the expected outer products equals the identity, and the expected norm is squared is less than or equal to epsilon. Then there exists some assignment for which the norm is less than or equal to 1 plus 3 square roots of epsilon. OK, now, so here's KS2, finally. Probably should have appeared a lot earlier, but this was our original goal. And what is KS2? It says that there exists some universal constants, eta and theta, such that the following holds. If W1 through Wm are complex vectors, the Wi are less than or equal to 1 in norm, and the measure against any u is eta. That essentially means that the sum over the Wi transpose is the identity times eta for all unit vectors. Then there exists a partition of the vectors into two parts, S0, S1, so that this, which is essentially the norm of the largest eigenvalue of the sum of the outer products in each set, is bounded away from eta by theta. So I don't miss any directions.
This is where at some point it's connected to expanders, right?
At some point, this is connected to expanders.
Is it this eta minus theta or eta positive?
No. So this part is not really. So in this, you need your random vectors to be choices of edges. So there your vectors are going to be edges. And essentially you're going to, partition them into two groups such that each group is, so if your original thing was a nice expander, each group is going to be an expander as well. So you're partitioning your edges into two pieces such that when you look at this collection, it's an expander, and this collection is also an expander. So we want to get really close to 1/2. This only requires you to be some constant away from 1, essentially. So if you could, the proof would go through with, 1.9 or something like that, or KS2 would at least. This is KS2. The 1/2 is essentially what was at the heart of KS2. You're trying to get far away. You're trying to get something that approximates half the identity, but what KS2 needs for the approximation, it just needs that you're bounded by some constant away from 1 times the identity. Okay, so here's the proof. So I'm given these wi's, and I'm going to form random vectors. So here's where my notation goes astray. I promised that everything was going to be in dimension D. These are going to be in R2D. And my random vector is going to take one of two values. It's either going to be wi with zeros under it, or it's going to be zeros with wi under it. And then they're scaled so that and I'm going to pick each one with probability 1/2, and I'm scaling it so that epsilon is what it needs to be. And so these satisfy all of the conditions of our lemma. So sigma, so we're guaranteed that there's some sigma which has the bound that we have from our main theorem. So take that sigma and form the collection the way that you would think. All the things that were assigned as 0, you put into set 0. And all the things that were assigned 1, you put it into set 1. And by the theorem, you have that this matrix, which is M0, M1, or M0, I minus M0, or I minus M1, M1, has largest eigenvalue at most 1 plus 3 square roots of epsilon, where epsilon was R2 over eta. We already did that. And we already did that. And the idea is that, so here your largest root is, like you were saying, the smallest eigenvalue here is bounded using the largest eigenvalue there. And so setting eta equals 32 gives you KS2 for theta equals 4. And if you use the stronger original theorem, you can get eta equals 18 and theta equals 2. And Casaza has shown that eta equals 2 is not possible. So the optimal answer lies somewhere in between. Okay.